This is Russell Ulbrich. I recently met with David Marsolais, a professor at the Université Laval and researcher at Quebec's Heart and Lung Institute in Quebec City.
No.
I wanted to ask you if you wouldn't mind introducing yourself in what your role is, maybe in at the University of Laval, and also in collaboration with people around you, because I understand that this is a core facility. So
Yes. So, well, my name is David Marsolais, and I'm a full professor at Université Laval, Department of Medicine, and I'll do full-time research at the Heart and Lung Institute in Quebec City. So basically, I'm interested specifically in lung disease, but of course, being Heart and Lung Institute, we have collaborations with people working on cardiometabolic disease, and also clinicians. And so we have a very integrative team of scientists here. And so, so when we design a platform or we acquire an apparatus, we have to keep that in mind, that it's going to be used for many people. So, I mean, I do my own research in my own lab, but when I acquire an apparatus, I have to take in consideration the needs of my colleagues. And so that's why we went into the building of this system that could be upgradable and tweaked to a range of applications, from the very difficult lung imaging to the easier soft tissue imaging and spleens and such, and also to the brain.
it was very interesting to me that it took you as long as it did. You were as patient as you were to find a two-photon microscope that met your needs. So I wanted to ask if you could describe that.
Yes, yes. So, I have to go a bit into the why and how I got to this point, being a full professor at Université Laval and doing lung biology and immunology. And so, so early 2000s, well, yeah, mid 2000s, I was at TSRI, and I was lucky enough to collaborate with Melanie Mathieu. She was a postdoc in Michael Cahalan's lab, who provided like amazing multiphoton imaging of the immune system. And so, so we had a couple of collaborations together, and we imaged lungs. And it was actually Ian Parker's multiphoton, which was, you know, self-built, right? And the video rate multiphoton was amazing. Post-its everywhere. You know what I mean? And so I knew that kind of system could be built. And so when I left Scripps and got hired here in Quebec City, so I mean, I felt like this was, you know, this was an essential part of the equipment. Someone who wants to do immunology, you need that. And so I started looking for all-included options with providers. I'm not a builder. I don't have any engineering experience. Really, just doing biology and immunology. And so I contacted all the big providers, and so that was 2009, right? So when I started looking for these, and it was difficult because the price tags were so high compared to what I knew could be built for my specific needs. And plus, it was difficult to find just the system that was just narrowed down to the version of the system that would respond to my needs. And I mean, there was always this moment when I was discussing with representatives where I was like, okay, we understand your needs, but you really need to get this too, because that's the future. And I mean, maybe for some other applications, but we're doing cell level imaging, video rate live imaging. And so it took 8 years. Well, I guess it took Blick to find the solutions I needed, which were having someone in front of me saying, you know, that's what you need, that's what we're gonna build for you. And that's when I started working with Blick to build my system.
I know one of the challenges that you have is that you're working with lung, and I wanted to ask if you could describe a little bit about how some of those ideas from other people have been brought into the picture to help you with your two-photon imaging.
Yes, yes. So other groups perform successful live imaging in the living animal. I mean, imaging of the lung. I mean, I'm not quite there yet. I mean, what we've been doing in the past is lung explants. And so we could, I mean, it was sufficient for our needs. But of course, like the most difficult thing you probably can imagine is imaging the lung, because, I mean, the movement is huge, right?
Yeah.
And then you have to take that into consideration. So we needed to optimize the system. And so we knew other groups designed, suction chambers, suction windows that you can use to fix the tissue. And so we needed to control the ventilation, being able to block breathing at very specific times to acquire. And so like working on lung physiology and biology in rodents. So we have this system. It's a very good system. It's the flex event apparatus. It's made by CIREC. And I mean, it allows you to perform measurements of, let's say, lung biomechanical properties, but it also allows you to control the breathing, right? And so the big task for us, and that's when the collaboration with Blick worked great, because we were able to work in collaboration with Blick to design the interface so that we could actually synchronize the image acquisition with controlled breathing from the flex event. In an environment where we need to image quickly in a tissue that is immobilized, so we needed to have rapid acquisition, trying to and volume acquisition would be good too, because if we have, for example, rare cells, and we can image a volume and bring it down, and that's the axicon, and narrow it down to an image, so I can image multiple cells in the same environment rapidly. And of course, speed is a huge aspect of the implementation of such technologies for what we want to do. So so far so good. I mean, we're trying. So the experiments we've done so far, we designed a negative vacuum chamber into which we can place lungs, and it's sealed, but it's controlled by the flex event. So we can reproduce breathing patterns. And so far we were able to, because we're still in the implementation phase, and the system is fairly recent, but we were really able to clean the images very well and have a crisp definition using that kind of approach. And so
did you have a custom vacuum chamber built as well? Was there something unique about that for you?
Yes. So in order to implement live imaging of moving lungs, so we decided we would go by steps. So right now, I mean, we're in a situation where we cannot accommodate the system right now at our center, because, I mean, this is an old building and it's always being remodeled, and we're actually waiting for the room. So luckily enough, so Blake had a room for the system. And so like, it's complicated to work with live animals when you're not in your own building, right? And so because of the ethics and all the approvals. And so we decided to go gradually. So we started imaging just explanted lungs. And then before going to live animals, we figured if we could reproduce, which would be probably the most challenging part of the project. So the lung is moving in 3D, right? The idea is to fix it at one point and have the rest moving in another direction. That's when you want to reproduce in the mouse, in the live mouse. And so in an attempt to go towards that, so we designed a negative vacuum chamber into which we can place the lung and have it connected to the flex event. And so the negative chamber acts as the thoracic cage. And so it keeps the lung expanded, but we can still adjust that and make it moving realistically enough that it reproduces movement in the rib cage.
Okay.
And so using that system, we were able to design the interface for image acquisition between the flex event apparatus and the Nirvana and the multiphoton microscope. So that's how we went for it.
I'm curious to know if you've had any further thoughts about directions that you might take in your research with the instrument, and maybe capabilities that you'd like to see that might support new work in the future.
Well, I mean, I have to start, by saying this system. So we acquired this system because we were able to design it in collaboration with Blix engineer to be as flexible as possible.
Yeah.
I mean, this is Heart and Lung Center in Quebec City, so we have all sorts of preps. I mean, we go from metabolic disease to cancer, and we also do immunology, and there's also brain research. So we needed the system to be as flexible as possible. So the first needs was to get this apparatus and all of the platine, all the environment around the objective to be as plastic as can be, because I mean some people are gonna want to do brains, spleens, skin, mucosa, and so that's the primary objective with the system, was to have it as open as possible. And of course we aim for the most difficult. So if it can work for lungs, it's probably going to work for anything else, right? Because lung is the most difficult. But if we can do live lungs, well, we can do live spleens, And so that was one of the important aspects. We're a good research center, but it's not huge, and we have to have our platform start so everybody can use it and can use it efficiently. And so that's one thing. So if you have something that's super high tech, it's never used, well, it's useless. See what I mean? So we have this very refined but narrowed down system that everybody can use, will be able to use when it's ready.
So you're gonna see a lot of different uses for the instrument. That's important. One thing I wanted to say is that when I first learned about the VMS, I learned about how it was originated at Massachusetts General Hospital, and Charles Lynn was sort of the genesis of the instrument. And it was interesting to me how it's utilized there, and that he has several of these instruments and he tears them down regularly and rebuilds them to suit the applications that are on the table at that time. So it's sort of a testament to the high degree of flexibility of something that's actually on the table, could be disassembled and reconstituted in any way that you need. So you have great, opportunity there.
And what I wanted to say also is, and because with fluorochromes available to use in vivo, and in collaboration with Blake, so we built the system around a laser that was optimized for our needs. And so we have this 2-line laser that can excite, let's say, red fluorochromes, and then the other line that is tunable. And so the system really allows us to get good signal in the red spectrum, and because it needs a strong excitation, but also we can just go everything else easily because the second part of the laser is tunable. So this is something that that we had in mind when we designed the system.
The flexibility of excitation, different excitations.
Yeah.
Yeah.
And can be upgraded, right?
Right.
To more channels. So that's an important part.
All right. Well, listen, David, I want to thank you very much for joining me today for this discussion, and I look forward to hearing more about your work with the VMS.
Well, it was my pleasure, and I mean, I enjoy so much working with Blake. I mean, it was really I was happy to take the opportunity to do that with you.
Thank you, David.